Okay, so in this lecture we will talk briefly about normed linear spaces. Okay, normed linear spaces. Okay. So the two things which we require to discuss the concept of a normed linear space is typically vector space and a very basic concept of a topological space. Okay, topological space. So let me just discuss very briefly, right? So a vector space is a certain additive abelian group. So V is an additive abelian group, such that a certain scalar multiplication is defined on it. Okay, such that a certain scalar multiplication is defined on it. Okay, scalar multiplication is defined on V. How do we do that? We consider elements of V and we choose a field F. We choose a field F. Our basic terminology is that if any element alpha is from F, then alpha is said to be a scalar. Okay, so V is an additive abelian group, as I just said. So V is an abelian group, additive abelian group, and for all scalars alpha, that is elements from the field alpha, and for all vectors V, elements from this space V are called vectors. So we define the scalar multiplication as firstly that it's closed. So alpha times V is in V. Next we have for two scalars alpha 1 and alpha 2 times V can be written as alpha 1 V plus alpha 2 V. Next we have alpha times V1 plus V2. This is alpha V1 plus alpha V2. So distribution happens from both sides, right? It happens in case of the scalars as well, and it happens in case of the vectors as well. Next we have, suppose you have two scalars, so alpha 1, alpha 2 multiplied to V. So this has a certain associativity attached to it. And number 5 is that the multiplicative identity of the field, it acts as the unity for the vector space. Okay, so if these five axioms hold in terms of scalar multiplication, V is given an additive abelian group, then we say VF is a vector space. Okay, VF is a vector space. Right. What is the concept of a topological space? So that's also quite trivial to do. Suppose you have a non-empty set X. Choose a non-empty set. Okay, X is a non-empty set. You can also choose X to be empty, but that's a quite trivial case. You will automatically understand the fact. Or let me just do one thing. Let me just take X to be arbitrary. Let X be a set. Okay. Then a subset of the power set of X is said to be a topology. Is said to be a topology on X. If these properties hold, number one, the empty set and the whole set X is contained in tau, should be elements of tau, because it's tau by definition is a collection of sets, so these should be elements of tau. Number two, if you have an arbitrary family of if you choose an arbitrary family of elements from tau, let a alpha be in tau, where alpha is some indexing set. Okay, so alpha is some indexing set. Uh, yeah. Then the union of all these elements are also in alpha. Sorry, also in tau. Okay, this is called closed under arbitrary union. Tau is said to be closed under arbitrary union, and analogously it's closed under finite intersection. Okay, so suppose let a I be in tau such that I belongs to block n. Block n is the set of elements 1 to n. Okay, then intersection of over I is equals to 1 to n. A I is also in tau. So then tau is said to be a topology, and if tau is a topology, then we say X along with tau this to be a topological space. Said to be a topological space. Clear? Okay. Um, Having done this, yeah, one more thing to just say it here, that every element of tau is said to be an open set. If U is in tau, then U is said to be an open set of X. Clear? Okay. So what we do is typically we now let me get to straight away to the concept of a normed linear space. So what exactly happens is that I consider a vector space. Okay. So let X be a vector space. Let X be a vector space over the field F. Okay. Where ordinarily we choose F to be either the set of all real numbers or the set of all complex numbers. Field of all real numbers, field of all complex numbers, whatever. So X is a vector space over the reals or the complexes. We try to define a function on X. Let n be a function from X to R. Okay, such that this function obeys certain properties. Number one, that the image of every element from X, or I can use the term vector now. So the image of every vector is non-negative. Okay, so nv is greater than or equal to 0 for all vectors, and the image should be 0 if and only if the vector itself is 0. Okay, this is the first property. Number two is that the image of any scalar multiple of the vectors is same as mod of alpha times the image of that vector. Okay, and such that so this happens for all vectors and scalars. Okay, and number three is that the image of sum of two vectors is less than or equal to the image of each individual vector, sum of the images of each individual vectors. And that's a very famous inequality. It's called the triangle inequality. Okay, let me name these axioms as, let's say, this is n1, this is n2, and this is n3. Okay, so if n satisfies the above axioms, then it's said to be a norm. It's said to be a norm, and we then denote the function n as this symbol. Okay. Here goes the element. That is, typically speaking, n of x is like this. Clear? Okay. So, and in that case, the structure of this vector space along with this norm is called a normed linear space. It's called a normed linear space. Clear? Okay, so this is the definition, very basic definition of a normed linear space. And let me just go through some quick examples. Some very quick examples. Example one is your usual real field R with respect to which we this norm we usually call the one norm, or we often call it the standard norm as well. So let me just use the term the standard norm. So such that so x is nothing but the absolute value of x. Okay. So this is pretty trivially a well defined norm, because we already know the proof of the triangle inequality in case of in case of the absolute value function. That's +2 level maths. It's we know that the absolute value function is always non-negative, and it's 0 only if the element inside is 0. and any scalar multiple can be distributed, right? So alpha times x, alpha belongs to R or C, so it's just the absolute value function just splits. There's nothing much to work out here, right? But this is indeed a very simple notion. Um, Let us check one more thing. Yeah, number two. These are some well-defined norms. Okay, consider Rn. Okay, so over Rn we can define a number of norms. We usually denote these norms as norm P norm. We call it as the P norm, and the P norm is defined in this way. So let x be equal to the n tuples xi be an element from Rn. Then we define the norm P norm of x to be summation over mod of xi, I obviously ranging from 1 to n, mod of xi to the power p, and this whole sum to the power 1 over. Okay, this is called this is the definition of the P norm. Okay. And so p can usually p can vary from 1 to not getting infinity. So p is a finite number starting from 1. So p, yeah, this will do. So it's obvious that what is the one norm of p? So the one norm of p is simple summation over mod of xi. So if x was an element from R, so this norm 1 is nothing but the standard norm, right? Then we have one very important type of the p norm, which is the 2 norm. 2 norm, which is obviously defined as summation over mod of xi squared whole to the power 1 by 2, I ranging from 1 to n. This is called the Euclidean norm. Now this norm is quite relatable, right? Because if you consider the R2 plane, okay, suppose you have a point here, you have a point here. Suppose this point is x equals to x1, x2. This point is y is equals to y1, y2. So we to choose 2 points from R2, we join them. What is the distance between these 2 points? So simple distance formula, if you remember, then if this is distance is d, then we write d as x1 minus y1 whole squared plus x2 minus y2 whole squared and the root of it. Okay. One very important notion, or I should say, very important sense of the norm of a certain element is quite relevant to the distance of that element being considered as a vector from the origin. Okay. So what I'm trying to say is that the norm of a vector, the norm of a vector is the analog of its distance from origin. Okay. So like in case of vector spaces, we had kind of constructed vector spaces as a space which generalizes the properties of vectors. So the normed linear space, again, actually it's another sort of a generalization of vector spaces. It's not a complete generalization as well, because we are simply using vector spaces, but we are defining some more properties which are very analogous to vectors. For example, distance between vectors. So in this case, norm simply kind of resembles the distance of a certain vector from origin, or you can also say to be the magnitude of the vector. Like we know that if you have the R2 plane, this is a point, let's say x, you can construct a vector like this. Then the magnitude of this vector is simply the distance of it from the origin. So you can think of it that in that way also. Is clear? So this is called the Euclidean norm, because if you consider the R2 plane and you consider a point x equals to x1, x2, then the distance of x from origin is exactly of this form, right? Is exactly of this form. If you choose n equal to 2, that's quite relevant. And so it's this plane is called Euclidean plane. R2 plane is called the Euclidean plane. It kind of arrives from Euclid's geometrical thoughts, you know. So yeah, so from that we can think of this term as the Euclidean norm. So, because it's very analogous to the distance formula we use, or rather I should say it's very analogous to the vectors, the distance between vectors, or yeah, so distance between vectors on over the R2 plane or over the Euclidean plane, right? Okay. There is one more norm which can be defined on Rn, which is also quite easy. Okay, one more thing. Let me just discuss it here. That uh, if you want to show that indeed the P norm forms a well-defined normed linear space, that is Rn. This is a normed linear space. So the first two properties are quite obvious, right? That it's non-negative and it's zero only if each of the components xi becomes zero. So that indeed means x becomes zero, and the scalar multiple part is also quite trivial. The triangle inequality is actually a very well defined inequality which is called the Minkowski's inequality, which is called the Minkowski's inequality. Clear? So the Minkowski's inequality is actually the proof of the triangle inequality of a P norm. That's what I'm trying to say. I will obviously write that later on. Um, One more important norm you can think of over Rn is what we call the max norm or the infinity norm. Infinity norm is a term which is not that used. We often call it the max norm in this case, the max norm, and it's defined as the maximum over I is equals to 1 to n of the absolute value of each of these components. Okay, this is called the and the triangle inequality in this case it's very trivial. It is direct from the concept of maximum of elements, right? Now, obviously, we are talking very arbitrarily, so we are not going that deep into each of these discussions. We're just kind of going over the surface through these things. The main thing which I want to discuss is relationship between a non-linear space and two very important spaces which we have already studied. One is the metric space and one is your topological space. So the concept of topological space I have obviously introduced in the start of this lecture as well. So what's the relationship between them? That's what I actually need to uh, show. But before that, let me first do one thing, which is observe this inequality. Observe this inequality. That if you have the norm of x, the norm of x can be written as norm of x, norm of y plus x minus y. Then using triangle inequality, this is less than equals to norm of x plus y. Uh, so yeah, you have norm of no, sorry. So from here you have norm of y plus norm of x minus y, right? So you can send y in that side. So norm of x minus norm of y is less than equals to norm of x minus y, right? Similarly, you can do the same for y as well. If you do this for y, then you have norm of y. This can be written as norm of x plus y minus x. So this is kind of it gives you norm of x plus norm of y minus x. But norm of y minus x, you can take one common outside, you get its magnitude, right? So you get magnitude of minus 1 times norm of x minus y. So this implies norm of y minus norm of x. So this should be less than equal to, sorry. So this is trivial triangle inequality. Okay. Yeah. So norm of y minus x is less than equals to norm of x minus y, right? So this statement and this statement clearly states the fact that mod of norm of x minus norm of y is less than equals to norm of x minus y. This is another very important inequality. It's often called the reverse triangle inequality. Okay. Yeah. Okay. Now observe the following facts. Let X be a normed linear space. Okay. Let X be a normed linear space, and we introduce a mapping on X. How do we do that? Let D of xy be defined as norm of x minus y. So D is a well-defined mapping on, so it's maps x cross x to R, right? Okay, so we define a mapping like this. Observe that it has these properties. So property number one is that if dxy is always greater than equal to 0, because the norm of any vector is always greater than equal to 0. X is a vector, y is a vector, x minus y is obviously a vector by the closure property of the additive operation on x. So it's all obviously non-negative by the definition of a norm. And if dxy is 0, so dxy is 0 if and only if uh, x is equal to y, right? Because why does this happen? You can easily observe that if this happens, then norm of x minus y must be equal to 0. But if this happens, then you should have x minus y to be equal to 0, and that would give this, right? So you can just go equivalently on either sides, right? Okay. Number two, observe that what is dx of y? By definition, it's given as norm of x minus y, but you can take minus 1 common outside, right? So you can take it like this, sorry, now it becomes y minus x. So it is mod of minus 1 times norm of y minus x, but mod of minus 1 is 1, so it's norm of y minus x, and norm of y minus x is nothing but d of yx, right? And let's check property number 3, which is if you have dxz, then dxz is norm of x minus z. X minus z can be written as norm of x minus y plus y minus z. But using the triangle inequality, you can write it as norm of x minus y plus norm of y minus z. What is norm of x minus y? It's by definition, it's just d of xy, and it's d of yz. So you have these three properties. Doesn't these three properties make D a well-defined metric? D is a well-defined metric, right? It's a well-defined metric on X. That is, XD is a metric space, right? I hope you guys know what metric spaces are, because I guess before reading the concept of a non-linear space, you should have read the concept of a metric space. So like I said, that the concept of a norm is sort of a distance between a distance of a certain vector from origin, analogous to this, while a metric is the analog of distance between two vectors. Okay, so these two analogs are kind of clear from how the metric is defined, right? So if x is a vector, if y is a vector, the distance between them is given as norm of x minus y, and norm is sort of the distance of a vector from origin. So I guess these two analogs are clear. So what conclusion can we draw out from here? So we can conclude that a norm actually gives a metric as well, and the term we use is that the norm induces a metric. Now, one thing which we have read in previous class, at least I assume we have read in previous class, is that any metric will induce a topology. Uh, Let me just write it again. Any metric induces a topology. Okay, induces a topology. How does it do so? If you have a metric space, you can consider what we call open balls. Okay, let me just give a brief introduction. So let XD be a metric space. We define what we call an open ball, defined for some element x in capital X and some positive r, uxr, which is defined as set of all the elements y from x, such that distance between x and y is less than r. Okay, so this is called an open ball of radius r and center x. Okay, these open balls, these are indeed open sets with respect to topology, but rather let's not talk about that. We have a definition for open sets in terms of metrics as well, but I am not going to try and discuss that in this lecture. Main thing is to focus is that the collection of all these open balls, x is in capital X and r is greater than 0, this generates a topology. This generates a topology. Generates in the sense the union of all these elements, the union of all these elements, where x is an element from x and r is greater than 0, these form elements of tau. So these form all the elements of tau. Okay, so tau is precisely the all possible elements, all possible union of these elements. Okay. In other terms, in terms of topology, this set is called the basis for the topology. Basis for the topology. Okay. Oh. This topology is also often referred to as the standard topology, which is generated by open balls. An open ball in case of the simple real field is nothing but an open interval. Okay. So the topology generated by a basis which consists of elements which are open balls is often called the standard topology. Okay. But we are not concerned about that. We are concerned about the fact that if we start with a non-linear space, then from the non-linear space we can induce a metric space. If you have a metric space, then by definition we can construct a topological space. So this topology is often referred to as the norm-induced topology. The norm-induced topology. Clear? Now an obvious question would arise that will the converse be true? That if you start with a topological space, you will eventually reach a metric space, or if you start with a metric space, you will eventually reach a normed linear space. So that's the question. That is whether the reverse uh, induction true. The reverse induction. Okay. So now obviously every topological structure cannot have a well-defined metric on it, and that's a very detailed course on topology rather. If I give a very brief hint to it, I should say that not all topologies are Hausdorff spaces. Not all topological spaces. Not all topological spaces are Hausdorff spaces. I won't try to discuss this in very details. Not all topological spaces are Hausdorff spaces. What are Hausdorff spaces? So if you have a topological space X, then X is said to be Hausdorff. X is said to be Hausdorff if you choose if for all pair of elements, distinct pair of elements x and y from X, there exists disjoint open balls u and v such that x is in u and y is in v. So if I just give a pictorial hint to what I'm trying to say, suppose this is your suppose this is your Hausdorff space. Suppose this is a Hausdorff space. Suppose you choose an element x from here, you choose an element y from here, then you will be able to construct open balls like this, which do not intersect and contain each of these elements. Okay. So not every topological space is a Hausdorff space, and one of the prime examples being what we call a co-countable topology. Okay. What we call a co-countable topology. So the definition of a co-countable topology is basically the topology consists of all the subsets of X such that it's empty or its complement is countable. Okay. Got it? Okay. Am I giving the definition right? If A is empty, no, I guess A should be X. Yeah, if A is X, yeah, if A is X or A complement is counted, right? Because if A is equals to X, so X obviously is in tau, and X complement is phi. Phi is assumed to be countable. Okay. So this is a definition for uh, yeah. So for what we call the co-countable topology. Okay. So okay. So that's what we have is that every topological structure or every topological space need not be induced by a metric. Okay. Is every metric space induced uh, by a non-linear space? Is every metric space a non-linear space? So we have a very fine example to this. We consider the metric space R2 and we define the metric D as e to the power x minus e to the power y. Okay, clear? Okay, so now this is clearly a metric. I guess I can just use the fact of R as well. Right? Yeah. Okay. So this is a well-defined metric, right? Right. Because from here you can say that it's an absolute value function, so it's always non-negative. And if it's equal to 0, then e to the power x must be equal to e to the power y, and e to the power x equal to e to the power y if and only if x equal to y. Furthermore, if you have dxy, then using the absolute value property, you can just reverse the statements to get uh, e to the power y minus x, and that will be give you dyx, right? And the triangle inequality is also trivial. Just add and subtract some e to the power z. It's very obviously uh, a metric space. But suppose it's induced by a norm. Suppose it's induced by a norm. Okay. Okay. Suppose it's induced by. Let me write it once more. Suppose it's induced by a norm. So by definition, d of xy should be norm of x minus y back then. So what can we say about norm of x? Norm of x is typically d of x0. So in this case, it should be mod of e to the power x minus e to the power 0. So it's 1, right? What can we say about the scalar multiple? Norm of alpha x. So this, I think, it will become norm of mod of e to the power alpha x minus 1, but it's obviously not equal to mod of alpha times mod of e to the power x minus 1. That is, it's not equal to mod of alpha times norm x. So this cannot be a well defined norm, right? This cannot be a well defined norm. Okay. So not every metric space is induced by a norm. Okay, you should be sure about that. And a very obvious answer to that should be also the fact that if they were all equivalent, then there would have been no concern about studying them, differently, separately. I should use the term separately. Okay. Okay. So let me go back to the. I guess I get the definition of a co-countable topology wrong. Um, yeah. So I guess the co-countable topology comes as the fact that is A equal to empty or the complement of A is countable. Yeah, I guess this is the definition. Okay. So, so this was all I wanted to discuss in this lecture. Or one more thing, I should just do it here, that the function norm is actually continuous. Okay? It's no this function on a norm linear space X is continuous. Why is it continuous? Now, if you recall the concept of sequential continuity, we can apply the concept of a sequential continuity in case of metric spaces. What does sequential continuity speak of? What does sequential continuity speak of? So it says that if you have a sequence xn converging to x, then fxn will converge to fx. This would mean f is continuous. Okay, so we can use this because sequential continuity holds well in metric spaces. If X is a norm linear space, so it's indeed a metric space. So we can use the concept of sequential continuity to show that the norm is uh, a continuous function. What we are intended to do is that we will choose a sequence xn from x which such that it converges to some element x in x. Then we will show that the norm of xn will converge to norm of x, and we are done. Right? How do we do this? Okay. What do we have by definition of convergence in case of a norm linear space? So let me just give you briefly explain that. In a norm linear space, a sequence xn is said to converge to some element x if for all epsilon greater than 0 there exists some natural number n naught, such that whenever n is greater than or equal to n naught, norm of xn minus x is less than epsilon. So it's quite analogous to the definition of convergence we have read in case of real analysis. Only the mod absolute value function there is interchanged by norm here. Nothing else. Okay. Okay. So let's start with the proof of this. So let this be star. Okay. So let's continue with star. So we have xn converging to x, right? Xn converging to x. By definition, this means therefore for all epsilon greater than 0, there exists some natural number n naught such that whenever n is greater than or equal to n naught, the norm of xn minus x is less than epsilon, right? But using reverse triangle inequality, it's obvious that the mod of norm of xn minus norm of x, this is less than or equal to norm of xn minus x, and norm of xn minus x is less than epsilon. Both of these are real numbers, so the definition in case of real analysis will follow from here because you have the absolute value function outside. So this obviously means that norm of xn will converge to norm of x, which will imply that the norm mapping is indeed continuous. Okay, clear? A structure, if you have a vector space, if you have along with a continuous function defined on it, such vector spaces are often called topological vector spaces as well. So a normed linear space is also called a topological vector, is an example of a topological vector space. I should be precise. Is an example of a topological vector space. Okay. Yeah. One more thing, I guess you should know about what complete spaces are. So if you have a topological space, in case of real numbers, what happened? Or I should say, in case of the real field, in case of the topology on a real field, standard topology on a real field, what happens is that if you have a convergent sequence, then that's surely Cauchy. If you have a Cauchy sequence, then that's always convergent, right? So, what is a Cauchy sequence? So let me just quickly define. So let X be a normed linear space. A sequence xn in X is said to be Cauchy. If for all epsilon greater than 0, there exists some natural number n naught such that whenever m and n is greater than n naught, they are arbitrarily close. The distance between xm and xn is less than epsilon. Okay. This is the concept of a Cauchy sequence. Now, if you consider the real field with the real analysis, you should say. In case of real analysis, what happened? We had considered the standard topology there to be the topology generated by all the open intervals. The norm is simply the absolute value function. In that case, recall that now every in an arbitrary space, every convergence sequence is automatically Cauchy. But the converse is not true, that the Cauchy sequence need not be convergent. It was true in case of R, in case of the real field with respect to the absolute value function as the non-linear, as the norm. Or in case of simple reanalysis, every Cauchy sequence convergent, right? So if you have a certain non-linear space such that every Cauchy sequence in it is convergent to some element which is in that very set as well, if xn converges to some x which is still in x, then x is said to be complete. Okay. X is said to be complete. So if X is an arbitrary topological space such that every Cauchy sequence converges in that very space, we say that topological space to be a complete topological space, and a complete normed linear space, a complete normed linear space is called a Banach space. It's called a Banach space. Okay. So at this lecture we have done this much. In the next lecture I might be bringing on more lectures on non-linear spaces, or any other important topic I feel of. Okay, so meet you guys in the next lecture.